Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to talk about area. We're not going to talk a lot about area, just enough to lead us into my second proof of the Pythagorean theorem. But the basic idea of area is we want to have an axiomatic treatment of the area, and we want to use it to make sense out of the area of a polygonal region. So for instance, this thing right here is an irregular pentagon, and I'd like to make sense out of the area of this thing. So a very natural thing to do is to slice it into some triangles, right, and say that the area of my pentagon is what I get by taking the sum of the areas of this decomposition into triangles. So that's the basic idea that we're going to use to axiomatize area. We're going to say that this decomposition property is a fundamental defining property for the area. And we will also have as a defining property that the area doesn't matter. Right? If I take two congruent triangles, so let's say this guy, and I have, let's say, some translated copy of it over here, the translated copy and that one have the same area. So those are going to be two of our defining principles. So let's go ahead and set that up in our axiomatic system. The way of setting up area in an axiomatic system, like our axiomatic system for Euclidean geometry, is to make area an undefined term. And then we normally associate to each polygonal region R a non-negative number that we're going to call the area of that polygonal region. And I'm going to write A of R to denote the area of the polygonal region R. And we're going to impose three axioms. The first one is if the region R is a union of two non-overlapping polygonal regions, let's say R1 and R2, then the area adds, right? So I can write the area of R as the sum of the areas of R1 and R2. Then the second area axiom is that the areas of congruent triangles are going to be equal to each other. And actually what we can do is we can build up inductively and say that a polygonal region, which is a region that can be written as a union of finitely many triangles, right? Then by the congruence of the component parts, we get that if I have two congruent polygonal regions, so two regions that are mapped one to the other by an isometry, then the corresponding areas are going to be equal. But that, I secretly proved a theorem for you. The axiom only asks this for triangles. And then the final axiom is that we define the area of a rectangle to be the length of the rectangle times the height of the rectangle. Or sometimes we call it length times width, whatever. There are two dimensions to a rectangle. The product of them is defined to be the area of the rectangle. And I'm going to say that's important here that we're emphasizing we're in Euclidean geometry. In particular, rectangles don't exist in hyperbolic geometry. Okay, so here let's illustrate how these axioms allow us to conclude what the area of a parallelogram is. So if we're given some polygonal region, so here my parallelogram, the basic strategy is we're going to cut it into nice pieces. We're going to move them around, and then after we do that, we get a rectangle or a union of rectangles. Okay, so what I do here is I take one of my vertices and I drop the perpendicular, and that gives me this red triangle here on the left. I now move that red triangle, right? I just translate it over to put it on the right. And as you remember from the various theorems you've proved about parallelograms, right, in this right triangle, it's not hard to show that this fits together exactly like so. Right? It's basically multiple applications of the alternate interior angles theorem. And now I have this beautiful rectangle here that I've highlighted in blue, and its area is going to be the base times the height, right? And I'm going to illustrate on here. That dimension is the height, and right, the base is that dimension, but right by the construction, the more reasonable way of thinking about it is that, right? So those are both the base, right? The shifted base and the original base of my original parallelogram. Okay, let's think about a triangle. So the trick here is we're going to do something to get a parallelogram out of it. And the idea is I just double my triangle, right? So I have here my light purple triangle, and I double it just by basically flipping over like so. This gives me two congruent copies of my original triangle. I have the original purple one, and then I have this sort of pink second one. I've dropped the altitude here because that's going to be useful for us. And now we apply the theorem about the area of the parallelogram to conclude, right? So we have 1/2 of the base, and the base here is this. And this guy is the height h. Okay, so now we've seen how we can use our axiomatic system to make sense out of the area of both a triangle and a parallelogram. So now let's think about worse shapes. I don't mean necessarily a value judgment of worse, but shapes that don't fit into our framework. So the most obvious example of something that is not a polygonal region, but that's a geometric object of great importance, is a circle. So we'd like to make sense of the question, what is the area enclosed by a circle? So for that, we need to think a little bit because it's not a polygonal region. So to make sense of this for the area of a circle, we need to extend the idea basically by taking limits. So this is something Archimedes did. I chose a nice round number here that was sort of the middle of his life, around 250 BCE. And what he did was he considered a limit of polygonal regions that were contained inside the circle, but that gradually filled out the circle as you increase the number of sides. Now, if you think about this a little bit, it's basically the same idea as Riemann sums that you use in defining a definite integral. It is exactly on the nose the same construction as you do in when you integrate in polar coordinates, if you remember back to Cal 2 when you did polar integrals. So now let's take a quick look at a Geogebra demo that gives us a proof by picture that the area of the disk of radius r is pi r squared. And we're going to assume that we already know that the circumference of my circle is 2 pi r. So here is the demo. And what we do is we take these wedges for our circle, right? So here I have 4 circular wedges, and imagine they're, I don't know, something like pizza slices, and you arrange them like so, where I put one slice with the crust facing up, another slice with the crust facing down, a slice with the crust facing up, one with the crust facing down, and so forth. Okay, so one of these slices we cut in half, and we had 2 half slices. Okay, so now what we do is we increase the number of pizza slices that we have. So now I have, let's say, 16 pizza slices. And what I've done is I now have, okay, so that's a half slice here on the left, but then we have 8 slices with the crust facing the bottom. These are the sort of lighter colored slices. And then I have 7 whole slices with the crust facing the top, and then that one slice that was cut in half. So we have these 2 half slices, one on either side here. And as you think about it, right, so let's think about the length of the crusts lined up on the bottom. Right, so I'm looking at the crusts of the lighter colored pizza slices. Well, that's 1/2 of the slices going around. So this length of the crust at the bottom is going to be very close to pi r. Right? As I make the number of slices more and more, that wibbly line here that I have at the bottom is going to get closer and closer to a straight line. Right? So that's a limiting argument. That's why I say this is a proof sketch and not a proof. Right? We need to make some argument about that behaves well. But right, if I take a small number of slices, I have a very bendy collection of crusts here. But if I go and make a large number of slices, that's very close to a straight line. And the length of the curved line is pi r. And now the height of it is the length of the slice of pizza. And the slice of pizza is getting very close to having the same height as the radius of my circle. So you can think of this in the limit as I take basically an infinite number of slices, that what I'm doing is I am making a rectangle, one side of which is pi r, and the other side of which is r. So this rectangle has area pi r squared, and so my configuration here where I stick the pizza slices, some crust up and some crust down, gives me something that gets very close to being this rectangle, and hence is very close to pi r squared. And in the limit then, we get actually pi r squared. And that's basically Archimedes' argument in a nutshell. Okay, that construction really looks an awful lot like Riemann sums, like you saw in Cal 2. And the remarkable thing is Archimedes was really very advanced on the way towards figuring out the ideas that then became the underpinnings of integration theory. So it's a shame he was killed by the Romans when they conquered Syracuse, which was a city in what's now Sicily. But these developments allow us, Archimedes famously found the volume of a pyramid, for instance, or of a cone. He also developed the area, the surface area of a sphere. He did a lot of really remarkable calculations having to do with geometric calculations involving area or volume. Anyway, that's it for this video. Thank you for watching. I hope you enjoyed it. Happy mathing.